Okay, so here are the solutions to the MYP5 circles test. First question, ABC points on the circumference of a circle, center O, AC is a straight line. Explain why ABC is 90 degrees. So it's because the angle in a semicircle is always 90 degrees. You've got the diameter of a circle, AC, making a third angle at the top, B. So B is in a semicircle. Angle in a semicircle always 90 degrees. Diameter of the circle is 3 centimeters. Calculate the area of the circle. So if the diameter is 3, then the radius is 1.5, and the area is pi r squared. So you just stick a radius of 1.5 into pi r squared. I did that on Desmos. I just screen grabbed from Desmos and pasted it into this. In fact, this whole document, I just took the original PDF file, screen grabbed it and pasted it into PowerPoint. And then this is just made from PowerPoint because I couldn't write in the original PDF document. So just for information there. So rounding to a sensible degree of accuracy, that's 7.07 centimeters squared. Next question. In the diagram, AB is a diameter of the circle and C is a point on the circumference. AB is 17, AC is 6. Calculate the area of the circle. Okay, so it is worth noting at this point that AB is a diameter of the circle. In other words, it goes through the center. So once again, we've got the angle in a semicircle at C, so that's going to be 90 degrees. But for this first bit of the question, calculate the area of the circle. So once again, pi r squared, diameter is 17, so the radius is half of that, 8.5, and the area is pi r squared, so just stick pi r squared with a radius of 8.5 into Desmos, and 226.98 and a bit, sensible level of rounding, 226.98, or even 227 would have been sensible there. Explain why angle ACB is 90 degrees. So as I said, because the angle in a semicircle is always 90 degrees. Then it says calculate BC. Okay, well, because that's a right-angled triangle, we can use Pythagoras on it. So the BC we're missing is one of the smaller sides. So it's a little bit small there, but I hope you can see BC squared plus 6 squared equals 17 squared. So it's the squares of the two smaller ones that add up to the square of the hypotenuse. So that's why we've got the BC bit together with the 6 in that equation. So tidying that all up, BC squared plus 36 equals 289. Take away 36 from both sides to get BC squared equals 253. And square root both sides to get BC is the square root of 253, which comes out to be about 15.9. So again, you can see I punched all this into Desmos just to do the typesetting. So it's given me these exclamation marks over there because it doesn't understand the things I've typed in. So it can't interpret that mixture of symbols and numbers and letters. But it was quite useful to use it just to set things out neatly in a quick way and then just paste it in. I could have cropped those exclamation points out, but I chose to leave them in just so that I could talk about how I did that. Okay, next question. A, B, C, D, and E are 5 points on a circle. ABD equals 58, so that's the angle at B is 58, as you can see on the diagram. BAE equals 85, that's also shown on the diagram. BDC is 19, that's also shown on the diagram. BD and CA, so the line from B to D and the line from C to A, intersect or meet up in the middle at N, and you can see that point N also in the middle of the diagram. It says calculate angle BDE, so the angle if you start at B, go to D and then down to E, the angle you get there. So it's the angle at D, in other words, the one that's not the 19 but the other one. Well, if you look at ABDE, ABDE is a cyclic quadrilateral. And when you have a cyclic quadrilateral, the opposite angles add up to 180. So the angle we're looking for and the 85 that's at A add up to 180. So BDE equals 180 minus BAE because of the cyclic quadrilateral, 180 minus 85, which is 95. So the angle BDE is 95. Then it says calculate the angle AND. So that's the angle in the middle there at N. If you start at A and then go up to N and then down to D. So it's the angle where my little cursor is at the moment. So there's probably a few ways you could have done that, but this is how I did it. I said that ACD is 58 because it's in the same sector as the other 58. Both of them come from the same 2 points, A and D. The angle DNC, which is very small there on the diagram, how I've marked it, but it's the third angle in a little triangle DNC. So that makes 103 degrees because the whole triangle's got to add up to 180. So I've just done 180 minus the 19 and the 58 to get 103. And then the angle we're looking for is just on a straight line with that 103. So angle AND equals 180 minus the 103, which is 77. So it's 77. Moving on. Okay, so we're looking for the area of a shaded segment. Well, the way to approach this, or one way to approach this, is to work out the area of the sector, which is the bit that looks like a slice of pizza that I've also shaded yellow in that smaller diagram. We've got 120 degrees. A whole circle would be 360. The area of a whole circle is pi r squared. So what we've got there in that little diagram is 120 360ths of pi r squared. And we know what r is. We know that that radius is 5. So 120 360ths of pi times 5 squared, which as you can see I've just stuck into Desmos and screen pasted it, a little bit over 26. Now I'm going to look at that triangle which I've shaded in purple or something purpley on that smaller diagram. Now we've got all the information we need to know to figure out the area of that triangle, because when you have a triangle in a circle like that with two sides coming from the center, then that's an isosceles triangle because two of those sides coming from the center are both the radius of the circle. And when you have an isosceles triangle, you can split it neatly into two right-angled triangles. And you do get a lot of exam questions with isosceles triangles that end up getting split into two right-angled triangles. So looking at that one I've shaded in blue there, it's got a 60-degree angle at the bottom because it's just half of the 120. And in relation to the 60, the side at the top, which I've actually labelled as the base, so I'm sort of imagining it turned round when I work out the base times the height for the area, that's opposite the 60. So what I'm going to call the base is the opposite side of the triangle. What I'm calling the height there is the adjacent side of the triangle, and then the 5 centimeters is the longest side, the hypotenuse. We know it's the longest side because it's opposite the 90 degrees. So we've got enough information there from trigonometry to work out the base and the height. So for example, sine 60 is opposite over hypotenuse. Sine equals opposite over hypotenuse. So sine 60 in this case is the one called base over 5. And I can multiply both sides of that by 5 to get the base is 5 times sine 60, which is about 4.33. And then for the height, so cos equals adjacent over hypotenuse. So in this case, the cos of 60 equals the adjacent, which is the height of the triangle, divided by the hypotenuse, which is 5. I can multiply both sides of that by 5 to get that the height is 5 times cos 60, which comes out to be exactly 2.5. And then The triangle area that we want is two of those blue ones, because remember I split the isosceles triangle into two right angle triangles. So the triangle area that we want is 2, because we've got two triangles, times a half times the base times the height. So that's the formula for the area of a triangle, a half times base times height. We've got two triangles, so it's 2 times a half times the base times the height, which comes out to be 10.825 and a bit. So that's the triangle, but remember the area we actually want is this yellow bit at the top, which is the difference between the sector, the pizza slice, and the triangle. So the shaded area that we want is the bit that was the sector, the pizza slice, minus the bit that was the triangle, and that came out to be 15.35 and a bit, 15.35 to a sensible level of rounding. Next question. A and B lie in a circle centre O. They are tangents to the circle. So remember, when a tangent meets the radius of a circle, and you've got radii of a circle there because they're both coming from the centre, that's 90 degrees. So the angle at A and the angle at B are both 90 degrees because they're a tangent meeting a radius. So that kite-like shape, OACB, is a quadrilateral. It's got to add up to 360 degrees. So the missing angle U is 360 minus the 124 and the 290s. 360 minus 304, 56 degrees. Okay, another question on the same page. It looks like a cyclic quadrilateral, but do note that only 3 of the vertices of that quadrilateral are on the circumference of the circle, and the other one is at the centre. So it's not a cyclic quadrilateral, but actually it's the rule about the angle at the centre being twice the angle at the circumference. You've got 2 points, A and C, and they're making an angle at the centre and an angle at the circumference. They're making an angle at O and an angle at B. So the angle at the centre is the reflex angle on the other side of the 3y. So it's 360 minus 3y, which is whatever that is. We don't know what y is yet, but it's the one that I've marked in yellow. That's the angle at the centre. The angle at the circumference is the 4y plus 4. There. So the 360 minus 3y in yellow is twice the 4y plus 4 because of the rule about the angle at the centre being twice the angle at the circumference. So I'm just writing that down. 360 minus 3y equals 2 times 4y plus 4. And we've got an equation in y that we need to solve. Multiplying out the brackets, 360 minus 3y equals 8y plus 8. Add 3y to both sides so that we don't have y on both sides. We get 360 equals 11y plus 8. Take away 8 from both sides to get the y's on one side and the numbers on the other side. Gives you 352 equals 11y. And then divide everything by 11 both sides to find out what a single y is. And it comes out to be that y is 32 degrees. Okay, moving on. In the cyclic quadrilateral, PQRS angle SPQ equals 78. So if we've got 78 there in a cyclic quadrilateral, then the 78 and the angle opposite have got to add up to 180. That's what a cyclic quadrilateral does. So it's because angles in a cyclic quadrilateral add up to 180. It's 102 because it's 180 minus 78. Okay, the next thing says angle PRQ to angle PRS equals 1 to 2. So another way of saying that is if PRQ is x, as I've marked there, then PRS is twice as much. 2x. So I've introduced this x to make it a little bit easier for me to interpret. So those add up to 3x, and we already know that that 3x is 102 from the previous bit of the question. 3x equals 102, x equals 34. Now the angle we're looking for is PQS, so the angle down there. And that comes from the same 2 points, S and P, as the 2x angle there. So the angle we're looking for is 2x, which is 68. Moving on. Okay, so we've got a lot going on in here. I can see cyclic quadrilaterals. I can see angles in the same segment. I can see angles at the center. So find angle ACD. So that's the angle at C. And it's going to be the same as the angle at B, because the angle at B and the angle at C both come from the same 2 points, A and D. So it's also 27 because angles in the same sector are equal. Then it says find the angle AOD, so that's the angle in the middle. And it comes from the same 2 points, A and D, as angle B does. So it's got to be 54. It's got to be twice as much, because the angle at the center is twice the angle at the circumference. Finally, the last one, angle AED. Angle AED is in a cyclic quadrilateral, A, E, D, and B. So it's opposite the 27 in a cyclic quadrilateral. So it's 180 minus 27, which is 153.